All right, onward, onward, more optimization. So should be pretty routine by now. Let's go ahead and get this one knocked out. So here we go. I have a rectangular page, contains 30 square inches of print. So this inside portion has 30 square inches of print. The margins on each side are 1 inch. So 1 inch on each side. I find the dimensions of the page that uses the least amount of paper possible. Okay, so I'll call this Y and this X. So the one thing that we do know is that X minus 2 and Y minus 2 will be that 30 square inches. You know that. The other thing is we want to know the least area, and that's just straight up X times Y for the paper used. Okay, let's get this ball rolling here. Let's solve for Y. Why not? So we got 30 minus X plus 2 in essence. So I'm subtracting off the X minus 2. And that's Y minus 2. And, excuse me, that is incorrect. I don't subtract that off. That's silly of me. I'm sorry. 30 over Y minus 2, because it's a multiplication. And then this would be X is equal to 30 Y minus 2 plus 2. So that is 30 plus 2Y minus 4 all over Y minus 2. Do just one more cleanup step on that. And so this is what, 2Y plus 26 all over Y minus 2. All right. That is that. Now we go ahead to the calculus portion of this problem. And that is the area. So that solved for X. So area is equal to 2Y plus 26 all over Y minus 2 times Y. So this area is equal to 2Y squared plus 26Y all over Y minus 2. Now, it's not the cleanest version, but whatever, it works. All right. So let's take the derivative of that. So the derivative of that is bottoms up. Derivative of the top minus, leave the top alone. Derivative of the bottom is 1. All over the bottom, squared. So this is what, 4Y squared plus 26 minus 8. So plus 26 minus 8 is what, 18? Minus 52 minus 2Y squared minus 26Y. So this is 2Y squared minus 8Y minus 8Y minus 52. All right, so critical numbers occur at 2. Okay, 2, and then wherever the top is equal to 0, I'll complete the square. So I'll factor out a 2, and I'll complete the square. So in essence, what I'm looking at is y minus 4y minus 26 is equal to 0. I'm going to, I GCF'd out a 2, and now I'm going to complete the square. So y squared minus 4y is equal to 26. So this is y minus 2 squared. That would require plus 4 in the previous step. And then, so this is going to be y is equal to 2 plus or minus root 30. All right. Yeah. Okay. So putting that on my area list here. So we have critical numbers at 2, and then I'm assuming it has to be the 2 plus the root 30. Yeah, 2 minus root 30 is a negative number, so it has to be the 2 plus root 30. So that's like 7.4 something. Okay, so that's the 2 plus root 30. Okay, so let's test this into the derivative. So let's take a small number like 1. Test this out. So this is 2x squared minus 8x minus 52. That should be all in a parentheses. Divide by x minus 2 squared. Okay, negative. Okay, a number in between 2 and 7, like 5 or something like that. Negative. And then bigger than 7. Positive. Okay. So this is a minimum right here. It's a minimum. That is what we're looking for. So find the dimensions of the page. Okay, so that means the height, or whatever, is 2 plus root 30. And if that's the case, I'm assuming the x is the same thing. Yeah, it'd be the same thing. So 2 plus root 30 minus 2 is root 30. I'm just going to look for the same number coming out of this. So this is the y. So x minus 2, 30 divided by that, plus 2. Yeah, it's the same thing as 2.
Yeah.
All right, so we got the dimensions of the page. All right, maximum volume. So rectangular packages sent by a postal service that can have a maximum combined length and girth, perimeter of the cross section. All right, of 108. Find the dimensions of the package maximum volume that can be sent. Okay. Combined length and girth. So perimeter. So perimeter in this case, we're assuming that it has a 4-inch, excuse me, a square bottom. So that would be 4x, and and length, which is y. Can't write numbers, I'm sorry. All right, so that's the 108. So it's the length and the girth. And then they want to know what will be the maximum volume. And so volume in this case is the base, which is x squared times the height, which is y. All right, so let's go ahead and go to work here. So y is equal to 108 minus 4x. Pretty easy peasy. We'll take that to the volume. So the volume is equal to x squared y, which again is 108 minus 4x. So this volume is negative 4x to the third plus 108x squared. All right, so that is the volume. Now let's take the derivative of that and see if we can maximize this volume. So the derivative of volume is going to be negative 12x squared plus 216. 216x. So that's the derivative. I'm assuming that I can take a 12 out of that. What do you know? So what I can do is I can take out a negative 12x, which would be x minus 18. And so since I'm in the business of getting that equal to 0, it can be equal to 0 or 18. We'll use that information to see if that actually does indeed maximize the volume. If it doesn't, then we have to do something else. But I'm assuming it will. So I'm testing this x versus the derivative of the volume, 0, positive 18. So I test a number such as the number 10. I put that in the derivative. Put that in the derivative, I'll get a positive number. Any number bigger than 18, such as the number 20, and that is a negative. So that is a maximum, uphill, increasing to decreasing. So that is a maximum. So the x dimension of this is 18 inches. That implies that the y is 36 inches, and the maximum volume is 11664 cubic inches. Beam strength. Wooden beam has a rectangular cross-section, height h with width w with strength s of the beam is directly proportional to the width and the square of the height. What are the dimensions of the strongest beam that can be cut from a round log with a diameter of 20 inches? Okay. Okay, so using the Pythagorean theorem, we know that w squared plus h squared is equal to 20 squared. I don't know if that really helps us out at all. Yeah, because we're going to be using s is equal to kh squared w, and so there's a bunch of moving pieces. What I'm going to do is I'm going to solve for h squared. So this is what, 400 minus w squared. Now I'm not going to solve for HH because I have an h squared that I can substitute. That's why I made the decisions that I made. All right, so S is equal to K h squared, which is 400 minus W squared W. I'm just going to get froggy and put this all together. So this is negative W, excuse me, as you were, K, which is a number, W to the third, plus 400 KW. Again, K is just a number, it's just a constant. All right. All right, taking the derivative of this, we have negative 3KW squared plus 400K. Okay. And we are looking to get that equal to 0, so I can divide both sides by K. That eliminates the K. And this is going to be W squared is equal to 400 divided by 3. 400 divided by 3. And so W is just equal to whatever the square root, what is it? 20 over root 3. I'm just going to leave it like that just for right now and get a rough idea what the heck that number is. All right, so this is approximately 11.5470. Okay, let's go ahead and test that out. So this is the W versus the derivative of strength, and we're testing out that 20 root 3, which is 11 something. So test a low number, such as the number 5, into the derivative. The derivative is negative 3W squared. Again, negate the K. It's 400K. Yeah, so that's a positive number. Anything bigger than that, let's test the number 15. It's a negative number, so that is indeed a maximum. Okay, so what are the dimensions of the beam? So W is equal to 20 root 3 over 3, which again, whatever, is inches, and I believe the, I guess maybe not the height, I don't know, we'll figure it out. The height is okay, it'll be something else. So I'm just going to give the rough answer. You can check out the work that I've done. I've done the actual analytic work to get it. So they're not the same thing. Yeah, so you can do the analytic work to figure out what that actual is as part of the fraction, but that's what it is. Okay, 50 elk are introduced into a game preserve. It is estimated that the population will increase according to the model, blah, 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 where T is measured in years. What is the rate of the population increasing when T is equal to 2? How many years is the population increasing most rapidly? That's a tricky question, that very last one. Dynamics. Okay, this is going to be kind of a calculator problem. Yeah, I'm going to kind of calculate this, use a calculator a bit in this one. So when is the population increasing most rapidly? Okay, so let's just start this off. Our population is 250. I'll write it as a multiplication. 1 plus 4e to the negative 1/3 t to the negative 1. So the derivative, multiply the outside. Negative 2 derivative on the inside is 4e to the negative 1/3 t times negative 1/3. So okay, so that is the rate. Okay, and so they're not asking us to maximize or minimize and things like, well, not yet. The first question is, what is the rate of the population increasing when t is equal to 2? So this is the rate of the population. The rate of the population, they want this specifically when t is equal to 2. All right, so what I'm actually going to do is I'm going to use the deriv function in my calculator and evaluate it too. So I'm going to go math 8, enter the original function. So I'm going to be taking the derivative of this, just in case I made a mistake. I know. Let's see here. I'm just going to type it actually just real quick. Okay, so with respect to x at 2, go backwards and insert my math 8. So this is the derivative at 2. And so that would be elk, and time is years. Now the next one is, as I said, more tricky. When is the population increasing most rapidly? So they are, in essence, looking for what is the rate of a rate? A rate of a rate. So that is the second derivative. And so what I'm going to do is I'm going to graph the second derivative and then figure it out from there. So the derivative being 1,000 divided by 3 e to the negative 1/3 t, big parentheses, 1 plus 4 e negative 1/3 t to the negative 2 with respect to x at every x. Go back to the front, insert a math 8. Did this problem before, so I'll just kind of help you out. -5. Let's go with like 30. Yeah, when it graphs the derivative, it does it relatively slowly. I'll check it out, but I got something else last time I did it. Oh, I know what I did. I know what I did. I know why it looks different. If I'm looking for a maximum of a derivative, if I'm looking for a max of a derivative, where I'm looking for it is, I'm looking for where does the second derivative turn from positive to negative. That's why I'm getting, I shouldn't have done this one, sorry. What I did is I just took the derivative of the original function. I graphed the derivative. So this is the rate. All right, so I graphed the derivative. Sorry about that. This will look a lot better. So again, this is a derivative. This is the graph of P prime. So this is the rate, and they want to know where is the maximum rate. Something like that. I don't know. What's that? But the maximum rate would be right there. That's the maximum rate. So I'm going to calculate the maximum. Yeah, the thing works a little bit slower when you're working with the derivative idea. So this occurs at 4.1588, comma 20.83333. All right, this is the time of the maximum rate. The other one is the rate itself. Sorry about that one, took a little bit more. Oh, that's it.